in Department of Electrical Engineering at National Cheng University, Taiwan. He received his PhD degree from National Kyoto University, Hsinchu, Taiwan. He has been awarded by the President of Taiwan for his outstanding research contribution during the tenure of his doctorate degree. He has worked as Principal Integration Engineer in Micron Technology, Taiwan, and as Postdoctoral Research Fellow at NTU, Singapore, and at NCTU, Taiwan. His current research interests include optoelectronic RRAM for neuromorphic computing, wide band gap oxide-based image sensor, transparent and flexible devices, artificial synapse, RRAM technology, and CMOS technology. In today's session, Dr. Dayanand would be delivering a talk on an artificial electronic synapse for neuromorphic computing application. So without taking much of the time, I would like to invite Dr. Dayanand to take the session ahead. Over to you, sir. Sir, you are not audible. Please unmute yourself.
Oh, okay. Can you hear me?
Yes, sir. Yes, sir. Now you're
okay.
on.
Thank you, Dr. Neha Kapoor. So we come share. Can you see?
Yes, sir. The slides are visible.
Okay. Oh, okay. First of all, I would like to thank you, Dr. Professor Ankur Cheng, who invited me as a keynote speaker. And I would like to thank you to today. I will start my presentation an artificial electronic synapse for neuromorphic computing applications. So actually, here is my presentation. Sorry, that one. Yes. So here is the outline of my presentation. If you see the introduction, my introduction divided in 4 categories. One is the overview of the non-volatile memories. Because in the semiconductor industry, there are different kind of non-volatile memories. So I will discuss on such kind of memories. And another one is the second one is the overview of resistive random access memory. Resistive random access memory is the non-volatile memory actually, and my current work or the current work on the resistive random access memory. Why I choose the resistive random access memory for the artificial synapse. And another what is the mechanism? Third part of the introduction of the RAM. Basically, I told you the resistive random access memory or memory stuff, both are the same things. So if we discuss on the RAM, so we will discuss on the conduction mechanism in the next slides. Conduction mechanism basically is not completely developed yet. Most of the researchers say it's based on the oxygen ion movement into the resistive switching layer between two electrode, and some people say this is the metal ion diffusion, but it is not complete theory developed yet. So we will discuss on the mechanism also. And the another thing is the why memory strip synapse for artificial, why memory strip RAM for artificial synapse. Why we choose artificial synapse for the neuromorphic computing application. Basically, the main things in the human brain, billions of the neurons are available, but every neurons are connected with synapse. Basically, there are two neurons. If you see one neuron connected with another neurons, and there is the one interface between two neurons, that is called the synapse. So in the biological neural subsystem, there is the synapse that's work for the data transmission from one neuron to another neurons. So that synapse, that transformation due to the calcium ion or sodium ions between two neurons. So in our artificial synapse also can do work like biological synapse. So that because in our case also we used top and the bottom electrode, and there is the one resistive switching layer between two electrode. In our case, either oxygen ion movement from top to bottom electrode or metal ion diffusion between two electrodes. So both the mechanism are the same. That's why we are using here RM as a artificial intelligence. And the next part is synaptic devices fabrications. What we achieved. So I will discuss also what we achieved so far in the memory devices or in the artificial synapse, and the summary of our presentation here. So here, if we come to the memory taxonomy in the semiconductor industry, if you see there are two kind of memories are available. One is the volatile memories. Volatile memory, if you see the different classes of memories, DRAM, the SRAM. The DRAM is the dynamic random access memory, and SRAM is the static random access memory. The DRAM currently people are working in the computer. This is the if you heard DDR3, DDR4 like that, this is the DRAM. This is the main memory of the computer. But the main problem is the volatile memory. If you remove the power, then data will gone. So you cannot storage the data after removing the power. But in this SRAM case, also the same problem. But the SRAM device is much faster than DRAM because it uses the 6 transistor to fabricate the SRAM devices. But it is much faster than DRAM. But it is expensive. So people are using DRAM only. And another class of memory, if we come in the non-volatile memory, if you discuss in the non-volatile memory, there is the two kind of memory, the charge storage. In the charge storage case, we come in the flash memory. Current people are using only flash memory. This is the mature memory actually. If you see the flash memory also divided in two categories, one the NAND flash and NOR flash. In the NAND flash is the mature one. So currently all people are using the NAND flash memory in our computer, mobile phones, and everywhere for the data storage. And the NOR flash also people are using, but the less part nowadays. So other memories, these memories, if you come here, the other memories, these are the emerging non-volatile memories. Emerging means these are the non-volatile memories, but these are emerging for future prospects. If you see the MRAM, magnetic RAM, PC RAM, phase change, resistive random access memory, FERAM, RRAM. But our topic is basically on the RRAM. RRAM is the resistive random access memory. Basically, resistive random access has a two part, the oxide-based RRAM. Oxide-based RRAM means the conductive filament formed between two electrode due to the oxygen vacancies. Because if you apply the voltage, the top or bottom electrode, so there is the conductive filament formed due to the generation of oxygen vacancy between the resistive switching layer. So due to the formation of the conductive filament, device can storage the data. So that is the part of the oxide-based RRAM. Another one is the CVRAM. CVRAM is the conductive bridging resistive switching memory. In this case, only Ag or Cu metal you can use as a top electrode, and if you apply the top, positive voltage on the top electrode, Cu metal ion can diffuse into the resistive switching layer, and they make a bridge to storage the data. So we will discuss completely in the next slides. So here is the key advantage why we choose RM only instead of another emerging technology or emerging memory devices. The RM has a key advantage if you see the scalability, because nowadays everyone want to the small size of the devices, because in the small chip in the semiconductor industries, if you see, or TSMC, Taiwan Semiconductor Manufacturing Company, Samsung, Intel, as well as Micron technology, nowadays they are working on small technology node. Even TSMC nowadays they are claiming 3 nanometer technology node. 3 nanometer technology node is very small size of the device. So how you will achieve this? So scalability is the big challenge for another this kind of memories. So if here you see the scalability, you can go sub nanometer range. RM has the big advantage because you can go to the sub nanometer technology range. So that is the good advantage for the future prospect if you want to make an artificial synapse or the future RM technology. So you can use these devices due to the good scalability. Another one is the endurance. Endurance is because everyone needs the high endurance. High endurance means the repeatability of the device, how long it can go. So the endurance is much higher compared than other memories. The speed also, if you see, the speed has the picosecond, so that is the much faster than other memories. CMOS compatibility, that is the important part. You can, the CMOS compatibility means you can use you can connect with a transistor, or you can fabricate this mass production. So with very small size. So that is the another important part. If you come to the challenges, there is because everyone has the advantage and disadvantage. For this memory has the need better understanding of the mechanism. Basically, I told you there is no specific mechanism actually, but people are claiming either the mechanism, the conductive filament form, or data can storage due to the either oxygen ions movement into the resistive switching layer, or the diffusion of the metal ion into the resistive switching layer. So we will discuss in future. So here the uniformity is the another challenge for RM. If you see during the continuous switching cycles, there is a wide variation in the set and reset voltage. That is another problem. So and another is the select devices. In the select device also, if you see, there is the problem also, there is the leakage path. During the continuous switching cycle, it shows the degradation also. So we will, but nowadays, researchers are working to remove these problems, and they are succeed also. So that is the good choice for artificial intelligence to use this device. So another thing, we come to the floating gate memory, because the floating gate memory, it is invented by the Simon Z in the Bell laboratories. The Simon Z is the actually inventor of the floating gate memory. In the semiconductor device and technology book, all over world, people are using this books written by the Professor Simon Z, and he is the current professor in National Chiao Tung University, and he was also my co-advisor and the thesis advisor during my PhD actually. So if you see the floating gate memory is just like a MOSFET. If you see the source and drain, but the main thing is here is the M2. If you see the M2 is the polysilicon layer to use the data storage, and this is the I2 and I1. If you see, these are the dielectric layer. This is SiO2. But is the problem during the continuous switching cycles. If you see here, data is storing and charging or discharging. If you see, so there is some leakage path. So after few cycles, it shows the degradation. That's why this memory not succeed well. But because nowadays so many memories came in the market, like NAND flash and all flash. So nowadays they are not using. But here is the many application of the floating gate memory. If you see here, the DVD players. Here is a lot of applications. But here, if you see the drawback and challenges of floating gate memory, here is the also leakage path I told you, because first they use the polysilicon to storage the data here, but again they use the SONOX. SONOX means they use the silicon nitride and high K dielectric like HFO2, MgO, Al2O3. These are high dielectric materials, but because the problem is the scalability here. Due to the scalability here, you cannot go in the sub-nanometer range, so you cannot reduce the device size. So that is the problem. If you are reducing the I1 insulating layer, so again the leakage path issue, so you cannot go in sub-nanometer range. Again, they also use the quantum dot, but they did not succeed. Here is the same problem because the scalability, you cannot go in the sub-nanometer range. So if you are reducing the size, that is the problem in this memory. So now here, if you see the non-volatile memory development trend so far, if you see the floating gate memory 2010 almost gone up to 30 nanometer. If you are going to in sub-nanometer or beyond the less than 30 nanometer, if you are see, so here is the old data actually, but nowadays if you see here in the Sonos and new memory. Now new memory means the NAND flash or NOR flash, but here is the NAND or NOR flash also another problem. After, if you see, you cannot go less than 6 to 7 nanometer. If you are going to reduce the size 6 to 7 nanometer channel length, there is another problem also. Here also the problem, the leakage path. So you cannot control if you are reducing the size or reducing the gate length size. So that is the main problem. So that's why people need a new memory or new generation of technology who can fulfill the industry demand to reduce the device size. So here, so people are thinking, so their device should have non-volatile. It should have flash memory like it should have like flash memory like NAND or NOR flash, and it should have speed like SRAM because SRAM is the much faster, and it should be high dense like DRAM. High dense means in a small chip you can make millions of devices, because nowadays researchers are thinking to make a high dense device, or there is the industry demand also. So all industries are thinking in the small chip you can make billions of devices. So you can connect the devices with the transistor for the mass production also. So here is the next generation memory. So it should be non-volatile effusion and long retention, and high speed as well as fast as SRAM. It means that the speed should have like SRAM and high density, because for the high density you can make the device layer by layer, so you can make 3D vertical array. So here is if you see the plausible candidate in the past decade, last few decades, researchers are working different kind of emerging technology devices. So there are the different memories, FRAM, if you see, and the STT RAM, phase change memory, resistive random access memory. So because these have the key challenges also, if you see the first three one, so there are many challenges, so that one cannot use for the future prospect. Only we have the choice, only resistive random access memory. So we will discuss here. If you see the prototypical memories, if you see in this table, if you see the FRAM, STT, MRAM, and PC RAM, if you see the scalability in the FRAM, the scalability is the main problem you see here. And the STT RAM, MRAM also is okay. PC RAM is good, really good. MLC, multi-level cells also you can see is a big problem for the FE-RAM. STT RAM also, this is the main problem. So PC RAM it's good. 3D integration is very bad. It is somehow is okay. It is good, but the post fabrication almost same in all three devices. Retention also almost same. Latency is good for this, and here you can see the latency is good for this one. And PC RAM somehow is okay. Power, but the main problem is the power. PC RAM somehow is good for the future application, but the power is the main issue in this device. So to remove these devices, only we have choice: resistive switching devices who can fulfill the latest demand of industry for future application, artificial intelligence, or as a memory devices. So here, if you see the comparison for the devices, so here is the all non-volatile memory devices. If you see here RAM, if we comparison the RAM, you can go to the 5 nanometer range. But currently industries are claiming, because this is the old data of 2013 from ITRS. Currently, companies are working on 3 nanometer node also. So 3 nanometer is very small size, because everyone want the small size of the devices. They want to make the high dense devices. They want to connect with RAM with transistor for the mass production. So, and the cell area is same for everyone. In the read current, if you see here, in the picosecond to nanoampere, picoampere to nanoampere, and write and erase time also you can see 1 nanometer range. But in the latest papers, the VLSI or IDM, I saw it is going to picosecond, is much faster than other memory device. Retention also, if you see 10 years, too good. Endurance also 10 to the power 12 if you compare it with another devices. So if you see here 10 to the power 12, and the write voltage 1 to 3 volt. But nowadays the researchers are already developed RAM that has the write voltage is less than 1 volt also. That is really good. The read voltage 0.1 to 0.2 volt, and write energy if you see here 150 FC. Here is the key advantage I already discussed. If you see the key advantage in my scalability, or already discussed previously: endurance, speed, CMOS compatibility, and key challenges also I already discussed. Need to better understand of the mechanism, because there is no proper mechanism so far. People are claiming different kind of mechanism, but basically there are two kind of mechanism still they are reported. So the RTN and improved reliability. Reliability improvement means the high temperature your device must have stable at high temperature. And select device also I already discussed, because we have to reduce the leakage path during the continuous switching cycles to stable the device. Here is the if you see the many application of non-volatile memories in the industry transportation, if you see, and industrial automation, smart meter, enterprise storage is the general memories and storage classes. That the different kind of, if you see the applications, wearable application on the smartwatch also you can see, and mobile application, tablet, mobile phones also, and mass storage memories, the NAND memory, if you see the because this is the mature one, so people are using as a mass production for the NAND flash memory. So here basically we come to the RAM, because our topic basically RAM or memory stuff for artificial intelligence system. So if you see, the RAM is the metal insulator metal structure. That is very simple structure compared than another memory devices. So in the metal insulator metal, so insulator might be HFO2, MgO, Al2O3, any kind of insulator you can use. Metal, Cu, Ag, and PT also, TIN and TI electrode. So here, if you see the mechanism, so it might be the device, this RAM device might be either bipolar or unipolar. If it is the bipolar, that is the different mechanism. If it is unipolar, that is the different mechanism. And the metal ion based only, this is the CVRAM. I already discussed conductive bridging resistive switching memory. So it can be Cu or Ag atom can diffuse into the resistive switching layer. So we will discuss in the conduction mechanism. So here is the conduction mechanism of oxide-based RAM. Oxide, why we say this is the oxide-based RAM? Because the filament is formed due to the oxygen vacancies into the resistive switching layer. If you see here is the fresh device. Fresh device, it is in the IRS state. It means that initial resistance state. Because initial resistance state, we did not apply any power for the device. If we apply the positive voltage on the top electrode, if you see here, and the negative voltage in the bottom electrode, resistive switching layer. This might be HFO2, MgO, any dielectric layer. So oxygen vacancies are generated into the resistive switching layer, and oxygen ion, this the yellow one are the oxygen ions, they move to the top electrode when you apply the positive voltage. And again, and this due to these reactions, if you come here, these oxygen ion accumulate at the top electrode, and that is the path is created. And in this case, device switch from high resistance state to the low resistance state. So that is the case of, or it means that you can say data is saved here or data is stored here between two electrodes. So this is the mechanism. And another case, if you see if it is unipolar device, what happens? If you use the unipolar or bipolar, if we are talking about the unipolar device, we have to apply the negative voltage also at the top electrode. The same. It is a set and reset, or data storage erase will happen in the one side, either in the positive side or negative side. If you are in the negative case, you have to apply the negative voltage on the top electrode again. So set and reset will happen in the one side. If you are talking of the bipolar device, you have to apply the negative voltage to reduce that to reset the filament or to erase the data. So you have to apply the negative voltage. If you apply the negative voltage, these oxygen ion again move back to the resistive switching layer, and they will recombine with the oxygen vacancy. After recombine with the oxygen vacancy, so here is the rupture of the filament. So data will gone from the device. So here again, if you want to set the device, you have to apply the positive voltage again. And again here you see, if application of the positive voltage, that oxygen ion will move to the top electrode again, and the conductive filament will form. So that is the proper mechanism of oxide-based filament. So if we come to the metal ion-based filament, if you see here, because in the metal ion, why we are talking of the metal ion only Cu and Ag can diffuse into the resistive switching layer. If you see here this curve, if you apply the positive voltage on the top electrode, the Cu is the top electrode here. If you apply the positive voltage, what happens? Cu atom becomes the Cu ion, and they migrate from top to the bottom electrode side. So, and here, because here we apply the negative voltage, and they recombine with the oxygen ions. Sorry, they recombine with the electrons and become the Cu atom again, and start to make a bridge here like this. And when bridge is completed here, and this device change its state from high resistance state to the low resistance state. Here you can see the complete filament is formed, and it means the data is stored between two electrodes. And if you want to erase this one, then you have to apply the negative voltage in the top electrode. So here in this case, you have to apply the negative voltage, or here also you see, if you apply the negative voltage, these again the oxidation happens here, and Cu atom becomes the Cu ion, and they migrate back to the top electrode, and here again the filament is ruptured. So on the other hand, if you think, because we in the positive case, we applied the compliance current actually to bound our device, because compliant current can control to our device for the breakdown. So if you, but then in the negative side, we don't apply any compliance current. So because if you apply the negative voltage, very high current pass through the filament, this filament, and due to the high current filament, because we didn't apply the compliance current in the reset side, so very high current will pass through the filament, and filament will be ruptured due to the Joule heating effect. This is the another mechanism to rupture of the filament here. So data will erase from the device in this case. So here is the achievement in the RM. This data from IDM and VLSI. These are the top conferences of our fields. The IDM International Electron Device Meeting, and very large devices. So here, if you see that this data is from 2010 to 2020. If we discuss here, so in the read current, if you see the 200 picoampere, it is really low. So that is really good for our devices. And speed, if you see the 300 picoseconds, compare than other devices, another emerging devices, it's much faster so far. Endurance, if you see 10 to the power 12, also you can see. And if you see the retention characteristic of the device, so our device or RM can be stable up to 10 years at 85 degrees Celsius also. That is the key advantage of the RM. Why? That's why researchers are thinking to integrate the device for the artificial intelligence system. So that is the big choice. That is good choice also for all researchers to go to the artificial intelligence system with this. That's why we also working on the RM to integrate with transistor to make an artificial chip to replace the biological synapse with electronic synapse. So here, if you see the artificial intelligence, there are many applications nowadays. If you first one is the strategic gaming. So, and another one is the speech recognition. Also, people are working on this. Another is the decision making, and the last one is the face recognition. So currently, actually, we are working on the face recognition application. So our work is only that one. So we will discuss on this work here. So why we choose actually? Why we choose RM only as an artificial intelligence system? Because in the current computer, why people are not using the current computer for the artificial intelligence? Why there is the main problem actually. If you are seeing the bus, this is the bottleneck issue actually. In the current Neumann architecture or one Neumann architecture, because currently all computers are based on the one Neumann architecture. So that is the big problem. Memory and CPU both are separate. So there is the one bottleneck. We say the bottleneck issue, because during the mass data storage, so need high power, and that this is the hanging problem, because in our human brain, the billions of the neurons, so you cannot use such kind of devices for the human brains, because you need high power, and there is that is not suitable for the artificial intelligence system, because in our human brain also neurons and synapse, they are connected together, but here is the gap because the memory and CPU are separate. So this computer cannot use for the artificial intelligence system. So here, so if we compare the conventional von Neumann architecture versus neuro-inspired architecture, so here we already discussed the bottleneck issue, but in this is the crossbar structure. Here is the neurons and synapse, they are connected together. But because this is the crossbar architecture, but if you see the crossbar architecture is like that, if you see, you can see my fingers, there is the interface. This interface is the synapse, and both my bottom finger is the presynaptic neurons, and the upper finger is the postsynaptic neurons. So that is this kind of a structure. So basically, because in this slides you cannot see, but this is structure is the crossbar structure. So you can reduce these issues because there is no gap. But in the von Neumann architecture, you can see the bottleneck issue. That's why you cannot use for the artificial intelligence. So here is the biological neuro subsystem. Here is the human brain actually. In the human brains, if you see the 86 billion neurons in our very small brain we have, and 86 billions, you know how much the neurons are available in our human brains, and every human brain human brains, the billions of neurons, they are connected with each other with synapse. Actually, synapse is the interface between two neurons. I already discussed actually, and that interface, what happened if you apply the voltage or some signals, if I am talking about the electronic synapse, if you apply the pulses, that strength is stronger. That strength is stronger due to the conductance. If conductance is increasing, it means that data is storing, or data is memorized in our brain. We can recognize or we can learn easily. But if this interface is weaker, interface means synapse. If interface is weaker, that we are forgetting. So we'll discuss about this in the next slides also. Here, if you can see here, this is the artificial synapse. This is the biological synapse. So this is the tails of the presynaptic neurons, and this is the dendrite of the postsynaptic neurons. If you see here, this is the small gap. This is the interface. Interface means this is the synapse. If you apply the voltage or something else, or for example, I tell you, if you dip your finger in the hot water, suddenly you shock, and that shock, and during that time, one neuron want to say to another neurons, see that my finger is burned into the hot water. So how it will say? So that will connect it. That interface will very harder, or you can say that conductance will increase at that time. That conductance will increase due to the calcium and ion movement. These calcium and ion movement due to the calcium or sodium ion movement. So that interface will be high denser, or you can say that will be conductance will be increased that point, and that transmit that first neuron transmit the data via synapse to the another neurons, and then we can think suddenly, oh, this is the problem if we put our finger in the hot water. So and the another things also, because if you see here is the presynaptic neuron, the postsynaptic neuron. In our electronic synapse also, if you see, this is the presynaptic neurons and postsynaptic neuron. We can use with these two electrodes, and here is the channel. Channel is due to the oxygen vacancy or oxygen ion movement. So that working principle is the same like as the artificial synapse. So we can correlate to each other. So that's why RM only the choice to replace the biological synapse with electronic synapse. And another thing, if it is the crossbar array, and you can make the high dense devices, and you can go to the sub-nanometer range for the mass productions. So that's why RM only or memory cell only the good choice to replace the biological synapse with electronic synapse. So if you come to the ideal characteristics of the synaptic devices, there should be the ideal characteristics should be like this. It should be the conductance should be increased linearly with pulse number, and this is the conduction is increasing. It means you are learning, and if you are going to forgetting, then it should be like this also. If you are using the different pulses. So here is the non-linear weight update. That is also important properties. So if this is the long-term potentiation, if you see the conductance of the long-term potentiation, LTP means long-term potentiation, and this one. So if it is linear, that means your device is really good, and the learning and forgetting will be good for your device. And the depression also, if you see, the depression is these things. And this is the potentiation below 1, and this is the depression. So this, if it is linear, it is going. If it is near about 0, it means that you can learn and forget the data easily. So that's why our device must have high linearity with pulse numbers. So here is our device fabrication. So if you see, there are many things to fabricate the devices. So if you see the sample preparation, also the photoresist we are using to fabricate our devices. Actually, photoresist is the photosensitive material to make our devices. So, and another thing, the you use the UV light to patterning the device here in the step 4, the bottom electrode. And if you are the ion milling, then here is the ion milling. After ion milling, you come to here and then lift off, and then completely bottom electrode confirm. And in the step 8, if you see the photoresist, again you have to, because you have to make a restitution layer also. And again we use the lithography process, and in the lithography process also. So here is the different things you can see, and here after that you go to the development, and that this is the bottom electrode also confirm. After bottom electrode, you do the electrode sputtering also again, and this is the complete devices. So this is the crossbar like this. So we'll discuss here. So actually, I choose the different kind of devices to make an artificial synapse here. So now I start my work here. First, I choose a TAOX-based device because this is the resistive switching layer, or you can say the dielectric layer. I use the 5 nanometer, and top and bottom electrode is ITO. ITO means indium tin oxide. Actually, these electrode both are very all are transparent, because nowadays researchers are working on transparent technology. So we are working also the transparent technology for the future artificial synaptic applications. So here is the switching mechanism or resistive switching devices. If you see here, the device shows the bipolar resistive switching characteristic. Or in bipolar resistive switching characteristic, if you see the set and reset voltage, during the set and reset voltage, these are the wider variation during the set and reset voltage. That is the problem in this device. And another thing also, the endurance is very poor. So if you see the endurance during the continuous switching cycles, first is the wide variation in the set and reset voltage, and the fluctuation on the resistance here also, high resistance state and low resistance state. In case of the high resistance and low resistance state, if you see the variation, that's why this device is not useful. And another thing, that this is the abrupt switching in both cases. So that device is not useful for the artificial synapse, because for the artificial synapse, there must have the non-linearity. But here is the non-linearity, because here is the abrupt switching, if you see. So if it is a linear, then we can use for the synaptic devices. So that device is failed for the artificial intelligence system. Now we change our device again. We use the GTO instead of TAOX. GTO means zinc doped tin oxides here. But if you see, so this is the non-linear on-off ratio. If you see the on-off ratio here, or you can see the on-off ratio is very small. And another thing also, this is only stable up to 500 cycles. It means that after 500 cycles, it shows the degradation again. So 500 cycles is not enough, because the RAM, they show 10 to the power 12 cycles or more than that in the AC endurance. So that's why this device is not suitable for the artificial intelligence again. So now we made the another devices that can fulfill the application for the artificial intelligence system. So actually we use bilayer structure, but because if you see, this is the abrupt switching, and here is the non-linearity is very good. So we decided why we are not combining together. So here we decide to combine both two layers together, and we made the bilayer structure here. And in the cross section TM image also, you can see TOX here and GTO, that one, and top and bottom ITO here. In the TM and image also, you can see here. Here all the bipolar resistive switching is the 10 cycles. If you can say here, this is the highly stable. There is no variation in the set and reset voltage. It means that device is usable for artificial intelligence system, because this here is the during the set and reset voltage, there is no variation. And if you see the DC endurances, both states are highly stable. If you see the LRS and HRS, both states are highly stable to 10,000 cycles. These are DC cycles. We will discuss in the AC cycles also. And if you see the transparency of the device, so you can see this device is fully transparent, and the transparency up to around 85%. So 85% is really good transparency for the device. So here is the multi-level states, because multi-level states are also necessary for the artificial intelligence system. So we got the 12 multi-level states. So if you see the different multi-level state, all states are highly stable up to 10 to the power 3 seconds without any degradation. So only we got the one LRS means low resistance state here, and HRS means this one. So different voltage. So we got the different multi-level states. So you can see here, and here is the cycle to cycle variation. Because cycle to cycle variation means, because if there is the cycle to cycle variation, so device is not usable for the artificial synaptic application. So here, if you see, this is the cycle to cycle. If you see the LRS and HRS, both states are highly stable without any degradation. It means that this device can use for the artificial intelligence system. This is the device to device variation, because some if you are checking, this is for the single device, because in the single device you can say, oh, there is no cycle to cycle variation. So that's why we choose the different devices from our wafer, because in our wafer there is 10,000 of devices. So we choose about 100 of the devices, because we cannot check a full wafer in one time. It takes around 1 year. So we choose randomly from the wafer to check the device to device uniformity. So if you check the device to device uniformity, so in the LRS and HRS, both states are highly stable. So that's why we decided to use the device for the artificial intelligence system. So here, so why bilayer device is highly stable? Why we are getting high stable endurance and another properties? So we can see the based on the XPS analysis. Here, if you see, is the top layer. In the top layer, if you see here, TAOX, the oxygen vacancies are 38%, and the middle layer, this one, the interface actually, this is the interface of both layer, 25%, and the bottom layer, GTO, if you here are the 45%. If you see the 45% vacancies and 25% as the interface, that's why due to the less oxygen vacancies, the filament is thinner here. If you because during the because this is the mechanism actually, due to the less oxygen vacancy, here will be the thinner filament. And again, if you apply the negative voltage to rupture the filament or erase the data from the device, so what will happen? Due to the Joule heating effect, that small that thinner part will be ruptured first, and device will change its state from low resistance to high resistance state. So that is the mechanism. So, and again things, because during the continuous switching cycles, that formation and rupture will happen at the particular point. So there is no variation in our device in bilayer. That's why we choose bilayer device to control the variation in our device. If you see the AC endurance of our device AC endurance, if you see, both states are highly stable, up to 1 millions. That is really nice, and that is applicable for the future artificial intelligence application. Retention also 90 degrees Celsius, because our device is fully transparent, and the 90 degrees Celsius, at the 90 degrees Celsius, both states are highly stable up to 10 to the power 4 or 10,000 seconds, and it can go up to 10 years also, because if you see up to here, there is no degradation, so it can go up to 10 years also. So here, if you see that synaptic characteristic, if you here is the potentiation depression, we use the potentiation pulses 0.8 volt for 1 microseconds, and depression pulses minus 0.9 volt for 1 microseconds. So this is the potentiation. Potentiation means you can also say this is the long-term potentiation, and you can it means the learning. This is the learning process from here to here. You can see the conductance is increasing, and if you want to erase the data from the memory or our human brain, or you want to erase the data from the synapse. So how to erase? It means that you have to apply the negative pulses again, and this means the conductance is decreasing. It means that the interface is going to weaker when you apply the negative voltage here. So this is the forgetting actually. So this means long-term potentiation. This is the long-term depression. So here is the non-linearity also another important parameter. I already discussed non-linearity should be around 0, but in our case non-linearity 1.8 for the potentiation case, and in the negative case also, if you depression also, this is the same like here. This is the depression also minus 1.3, but it is not equal to 0, but is near about 1 or 0. It means that you can say, so the device characteristics are really good. So in the picture C, if you see the repetitive 790 potentiation and depression cycle. Repetitive means learning, forgetting, learning, forgetting, learning, forgetting, learning, forgetting, learning, forgetting. So if you see here, our device, we shows here up to 790. Means it is really good for the artificial intelligence system. So we can use this device for the artificial intelligence application or artificial synaptic application in near future. So here is the image recognition. Because our work on the image recognition, this is the input image. Actually, we give the input image to our data, and this is the noisy data. Actually, noisy data. This is our data. This is our data from potentiation depression data here. If you see, this is the random data, and we use the Hopfield neural network to check the accuracy of our device. So this is the noisy data, is our data here. Again, so after some iterations, after 17 iteration, so it can recognize easily this image again. So this is the record picture, means recognize image, and the accuracy of our device is 98%. So that is the really good, actually, because 90%, 98% accuracy of really good for this device. So here's the table comparison. We compare our device with another devices or previous reported work. If you see here, our device is the one important thing. Our device is fully transparent, and if you see the potentiation depression, if 0.8 volt for 1 microsecond and 0.9 minus 0.9 volt for 1 microsecond. And here, so far only they shown 500 only, but in our case 790 cycles. That's the repeatability. So it means you can say, so learning and forgetting, it can go up to 790 cycles without any degradation. So here, if you check the non-linearity, non-linearity for our device is really nice compared than other one, and the transparency is this is a fully transparent, and it means that you can say this device is suitable for artificial intelligence system. Here is the summary of our device. So we discussed the single layer and bilayer devices, but our bilayer device is capable for the neuromorphic applications for the future prospect. And the long-term potentiation and depression, at least 790 repetitive cycles. That's why I told you that the repeatability, learning, forgetting continuously, it can go up to 790 cycles continuously. And we use the to check our image recognition. So we use the 28 cross 28 pixel. We comprising 784 synapse to check the accuracy of our device. So we use the but one pixel means one synapse here. And HNN can be successfully trained to identify the input image with the training accuracy of more than 90. Sorry, it is a 98%. So here is the mistake in 17 iteration. So thank you very much.
Thank you so much, sir, for such an enlightening session. As I can see few questions in the chat box. If you allow me, I can ask the questions one by one.
Oh, sure.
Okay, sir. So the first question is from Miss Mamta Patel. Why bilayer synapse has better performance than single layer one?
Oh, okay. Sure. Okay. Can you see here? Okay.
Yes, sir.
Can you see? Yes. Basically, because I discussed here, it is because in our case, conductive filament is formed due to the oxygen vacancies. So here, if you case in the top TAOX layer, here is the oxygen vacancies are 38%, and interface also, because we use the XPS. This is the XPS is from top to bottom. Top to bottom means depth profile of the XPS. In the top, if you see TAOX 38%, and the interface vacancies 25%, and the bottom ZTO is 45%. Due to this interface, because that the interface vacancies are smaller. If vacancies are less, the filament will be thinner here. And during the reset, because this is the set process, it means that set process means data is storing in the device when you apply the positive volt in the top electrode and negative volt in the bottom electrode. So data is storing like this. And this filament is thinner due to the less oxygen vacancies as the interface. But if you want to rupture or if you want to erase the data from the device, so you have to apply the negative voltage. Due to the negative voltage, because due to the Joule heating, I told you in the conductive filament part, because we don't use any compliance current, and application of the negative voltage here, very high current will pass through the filament. Due to the high current pass through the filament, thinner filament will rupture first. So that's why again, if you going to storage the data again, because only a small part is rupture, that filament will form continuously here, and that's why during the continuous switching cycle, filament will form rupture, forming and rupturing at the particular point here. So okay, and again I show you this slide. In the continuous, if you see the continuous 10 cycles data, there is no variation here. Due to the no variation, it means that filament is forming at the particular point. Forming and rupturing is happening at particular point. There is no variation. But in single layer case, if you see here, in the single layer case, the wide variation in the set and reset voltage. Due to the wide variation, the filament is not forming at the particular point. It's the forming at the different point. Due to the different formation rupture of the conductive filament, the device is not stable. So that's why we our bilayer device is much better than single layer device.
Thank you so much, sir, for such a detailed explanation. Moving to the next question. Why NAND gate can't be used to store mass? This question is from Priya Khandelwal.
Oh, actually NAND gate, this is the mature memory actually, because in the emerging technology, researchers are working to use the RRAM for the future. But there is the problem I told you in the first slides also. Here, sorry, because there is the challenges. Because people don't know people don't know in detail the mechanism actually for the RRAM. So if we don't know the mechanism and uniformity also, I told you the wide variation in the set and reset voltage and the select device leakage issue also in this case. And another things, if these are problem, because we are researchers are going to sort out these issues, but they are not completely resolved so far. So that's why NAND flash only mature device for the data storage so far.
Okay, sir. Moving to the next question. This is from Dhananjay. How researchers find out that device showing retention property up to 10 years or more than that?
Oh, actually, okay, show you. So here, so in this picture, if you see, because actually they guess 2 to 10 year. Basically, for the 10 year, first they put their device to continuously set and reset case. First they set and they do reset and they check first low resistance state if it is stable up to continuously 10 year. But 10 years is the too long time, so they guess. So they predict actually like this. In case we check up to 10 to the power 4 seconds, and there is no degradation actually. If you see in the both states, highly stable up to 10 to the power 4 seconds or 10,000 seconds. So if there is no degradation, it means that we can predict the device can go up to 10 years actually. So because 10 years is too long time, so it's very hard to check our device continuously. But researchers can do only based on their prediction. So in our case also, we say our device can go up to 10 years.
Okay, sir. Thank you, sir. I hope the query of the participant is solved. Moving to the next question. This question is from Mr. Hariom Nagar. Why TAOX-based device has wide variations in set and reset voltages?
Okay. Yes. Here. Okay. Actually. Okay. Here. If we see the bilayer device, if you can see, for example, if you remove because I don't have the single layer one filament model. Okay, I come to the here. I think it will be better to tell you guys. Oh, here. Okay, if you can see this picture, this is the filament model. Basically, this filament model is not like that. This filament model should be in the conical shape. due to the conical shape, if you see, because if you applied the positive voltage on the top electrode, oxygen vacancy move toward the bottom electrode and oxygen ion move to the top electrode, and the oxygen ion accumulated at the top electrode here. But in case here, because vacancies are moving to bottom electrode, so they will start to make a bridge from like this. So that bridge should be in a conical shape. Conical shape means that this filament should be thinner at the interface of top electrode, and the bottom electrode it will be thinner. But if you apply the negative voltage, what happens? We don't know how much ion will come back, and this filament sometimes rupture more and sometimes rupture less, because due to the variation in the voltage, due to the high variation, sometimes this filament rupture more, up to maybe it can rupture up to here. If you can see, sorry, I think I show you with pointer. So here, this filament can rupture more sometime due to the high voltage. If high voltage rupture here, then again you have to set the device. You need to high voltage, because if this filament is rupture up to here, so need higher voltage to form the filament again. And if it is fully ruptured, then again the variation in the voltage. So due to the wide variation in the set and reset voltage, this filament is not stable. So sometimes it can form here, sometimes it can form here, sometimes it can form here. So due to the instability of the voltage, filament is not stable. That's why single layer device is not stable in our case also.
Thank you, sir. Moving to the next question. This is from Mr. Lokesh Gambhir. What other oxides can be investigated to increase the reliability?
Yeah, another oxides also. TOX is a mature one so far. HFO2 also mature. MgO, they are working on MgO, and Al2O3 also. But so far HFO2 and TAOX is the better performance compared than other oxides. Actually, because and TAOX and HFO2 is the CMOS compatible oxides, because in the semiconductor industry like TSMC, Samsung, Intel, so they are working on that. So they are fabricating with TAOX and HFO2 for the future memory application. That's why, because for HFO2 and TAOX, the endurance is much better compared than other oxide materials.
Thank you so much, sir, for such an informative session. Now I would like to request Dr. Lokesh Gambhir for vote of thanks. Over to you, sir.
Thank you, Dr. Neha. Artificial synapse, an artificial electronic synapse for neuromorphic computing application. In fact, the floating gate memory devices and its application have been the key area of interest over the past decade across the globe. So on behalf of School of Applied Sciences and Center of Renewable Energy and Storage, I extend my humble gratitude to our keynote speaker, Dr. Dayanand Kumar. Thank you so much, sir. Dr. Dayanand Kumar from National Cheng University, Taiwan, for taking out your time in the holiday season. I understand that it's in holiday season. So thank you so much for taking out time for us and for providing an insightful mention to our sponsor. I extend my humble gratitude to the Honorable Management, Suresh Kanvia University, for continuous support and encouragement. Special thanks to respected conveners and associated faculties for the coordination of the lecture and the entire lecture series. 2 lectures are again planned in the future. A warm thanks and heartfelt appreciation to all the participants for their enthusiasm. I hope the session was insightful to you all and provided the glimpses of opportunities brought to your reach actually by the School of Applied Sciences, Suresh Kanvia University. Thank you so much. We'll meet again in lecture 3 pretty soon. Over to you, Dr. Neha, for the concluding remarks, please.
Thank you so much, sir. Thank you once again, Dr. Dayanand, for taking out time from your busy schedule for this session. I hope all the participants have taken note of the important points and interesting results also. Thank you so much, sir, once again. And I call the session closed for today. We'll meet again for the next session. Thank you, sir.
Thank you.